In this video, we'll go over the goodness of fit measures for multiple regression. Similar to the one-variable regression, SCR measures how spread out the underlying data are around the regression line. But different to the one-variable regression, now SCR incorporates the parameter K, which measures the number of regressors in the model. The denominator is now n minus k minus 1. So if we're using the squared residual divided by n minus k minus 1, which measures the degree of freedom in the sample, together they give us what is the variance for the residual. And taking a square root of the variance give us what is the standard deviation or the standard error of the residual, or SER. Also, for one variable regression, R-square measures, we also use R-square to measure the goodness of fit. R-square represents the fraction of the sample variation of the y variable that is being explained by the x variable. By definition, R-square is given by the explained sum of squares divided by total sum of squares, or ESS divided by TSS. And since TSS is given by ESS plus SSR, or the sum of squared residual, this ratio can also be rewritten as 1 minus SSR divided by TSS. And therefore, the smaller the SSR as a percentage of TSS, the higher the R-square, which means better fit for the data. However, there's one problem with using R-square for multiple regression. That is, as you throw in more and more regressors in the model, the R-squares of the model always increases, regardless of whether the additional variables are statistically significant or not. Even when adding a completely misleading or irrelevant variables into the model will increase the R-square of the model. And that's why for multiple regressions, we introduced another goodness of fit measure, the adjusted R-square. The adjusted R-squares will penalize you for including additional variables that don't make sense. The definition for adjusted R-square is 1 minus a factor times SSR divided by TSS. The numerator of the factor is n minus 1. The denominator is n minus k minus 1, which gives us the degree of freedom in the analysis sample. Now, if k increases, the factor increases, and the negative factor decreases, and hence the adjusted R-square together will decreases. And this way, if we randomly throw in irrelevant variables, the adjusted R-square will go down instead of going up, suggesting that the fit for the model is becoming worse. Now, the only way to increase the adjusted R-square is to reduce SSR. If SSR is reduced significantly compared to the previous model, then the adjusted R-square will increase significantly to signal a better fit for the model. In summary, a higher R-square or adjusted R-square means that more of the variation in Y is explained by the model. But neither R-square or adjusted R-square give any indication on whether our variables are unbiased estimators of a causal effect. Additionally, we cannot use R-square or adjusted R-square to draw statistical inferences. Whether regressors are statistically significant must be determined using hypothesis tests.